All right. So today we'll be building a simple like a graph interface, um, with the intention of creating like a graph drawing system in Python, naturally. So we'll start by just figuring out what I need to do. So basically, in essence, we'll just have basic class that we want to be able to create a node, create an edge between two nodes. For now, we'll keep it limited to just undirected. So none of this single direction stuff. Create an edge, create a node. I think in my mind, if I want to do a drawing, if I want to draw a graph being like this kind of graph with nodes and edges, not like this kind of graph. If I want to draw that, it probably makes sense in my mind. Like I was thinking about this before. I think what I would do is I would start at some kind of source node, whatever that means, and then I would run BFS basically, because I think BFS from memory would like detect all the edges. So it should be able to, and it would do neighbors first. So like it would draw one node, and then like it would draw the neighbors nodes with those edges, and then for each node in the queue, it would figure out what the next node to draw is, and then I feel like that would be like a more logical way of like making sure that nodes that are joined together are drawn together, and then like reducing the risk of like having a node like over here that gets close, like reducing the risk of this kind of thing happening where like nodes that aren't joined together are close, and then nodes that are joined together are far, and doing something like having a lot of spaghetti kind of thing. So I guess like having a BFS method would be good. Oh, ran out of memory. There you go. So yeah, like in terms of methods, creating a node, creating edge. I guess deleting would be good as well. Deleting stuff. BFS would be good. Do I want weights? At some point, not now. I'll write in red. Stuff that can come later, just off the top of my head. Directed, edges versus undirected, and then weights, including negative weights. BFS, we could do DFS as well for lols, just to practice, I guess. And if we do DFS, I'll do it iteratively. I've written plenty of recursive DFS, but iterative I tend not to because it's more annoying, slightly more annoying. Create an edge, creating stuff, deleting stuff, having the traversal things. Dijkstra doesn't really make sense until after weights. And then yeah, that should be enough, right? Surely. And then the question is, do I want to do like 2D array? Probably not, right? Yeah, probably not. Just do adjacency list, I think. Is there another way of representing graphs? Probably. We'll have like a list for each node. Ooh, do I want a list actually? Yeah, right? Then one of these. This could be a class in itself, to be fair. Like, it has the other vertex, plus, at some point I might want to add weights and stuff. And then it will have a next field as well to be able to hold the next guy. Linked list, basically. Yeah, an array that is a linked list. No, wait, an array of linked lists. But then the issue is if I delete, that could be problematic, right? So if I delete a node, then I have to delete the node from here and also from all the places it exists in the edges, don't I? Maybe it would be easier to do a matrix. Then it's linear time at least. Well, is it linear sum? Because I have to shift all these elements I have to shift up or something. I don't know how 2D arrays work. It's fine. Um, what do I want to do? I could do like the normal trick of like just using a dictionary and then but even then, like deleting from here is annoying. Okay, let me do other stuff for now. So in terms of a vertex, you're gonna need to give it like some kind of identifier so that you can differentiate quickly between two different vertices. That's pretty much it. And then edges would for now be two vertices, so it would be like vertex 1, vertex 2, and then yeah, this is where the weight would go as well probably. So these are different objects you can have. Yeah, deleting is more annoying than I first realized. I kind of forgot. Because if you do use an array, then the removal of a vertex and then removing it from all other places is a bit annoying. I guess normally in the very clinical sense, like how often are you deleting from a graph, you know? Like in the real world, like you're not going to delete a node overnight, but I guess you could if you make a mistake, kind of thing. Deleting. I think what I'll do is I'll have a single list, maybe a set. Okay. Yeah, I guess if your graph isn't changing much, then it doesn't matter if the modification uh, functions or methods are a bit more costly. But I just feel like surely there's a good way of deleting stuff. Like insertion, I'm not too worried about, and I could use the. I just feel like the kind of representations you get taught in school are like very specific to like you already know how many nodes you have, you already know what the edges are, and then you just have to create it. But like, it doesn't really consider deletion as like a important operation. But what if it was an important operation? What would you do? Am I forgetting something? Is this like really obvious? I should know this. I don't think I can help. I think what I need is a fast way of figuring out what edges there are. So what I could maybe do is have a sort of like a lookup table, I suppose. And then I'm able to find a vertex really easily from its ID or something. Whatever, let's just say it's a big array. And then if I delete, I just pop it off. And then the extra thing I do is I have to look through the edges that this guy will somehow join to and delete those edges from the set. So I guess like maybe in the vertex I have a set called neighbors, and I just for each guy that this dude was joined to, I delete from the set of vertices. Yeah? Is that gonna be easy? Is that gonna work as normal? Maybe, maybe not. I mean, it's gonna be pretty small application, so it's not like I need to be super. It's not like performance isn't actually a huge deal. I really feel like I can make this work normal. Like the idea being like if I'm gonna delete from this list, if it's a hash table, it will leave a tombstone. Oh no, tombstone. It'll leave like a tombstone. Wait, is that right? It'll leave like a gap in the array as opposed to like shifting everything down. I forget if these gaps get filled back in. I guess not, because what are you gonna do? But I guess you could have like a queue of like the gaps that you have, and then every time you have a gap, you enqueue it. But what if the gap is earlier? Well, it doesn't really matter as long as it's being held, right? No, what if it's a hash table? Then it will have its own hash function. Okay, maybe there's a maybe I should build a cool hash function first. One that keeps track of the gaps, and then and then every time you pop something off, it stores where that gap was, and the ID will actually be the index that you are. And so there shouldn't be any collisions because we're always making sure that the gap is empty before we put it in, so the ID is unique, and then you look it up nice and simple. Your neighbors tell you who is joined to you by the edges that were created. Every time you add an edge, each vertex set gets the corresponding neighbor, like each other as a neighbor. Yeah, and then every time you delete, if you're going to delete an edge, then you go to each vertex, pop each other off, delete each other from the set. And if you delete a whole node, then you delete its thing from the list. Add this gap to a queue so that we know to do that, and then to like we know that where the gaps are, and then for each vertex, for each neighbor, go to that neighbor and then delete this edge from that neighbor set, if that makes sense. So this is a strong assumption because we're really assuming that the edges are undirected, which is true for now. But if I was to expand and try and make directed edges, then you would probably need something like incoming versus going out, like two sets, so that you know like, oh, who's kind of going to mention this guy. But for now, it's not important. So I don't think I'm going to need this. I think what I'll do is, so first step one, hash table, which contains both the actual list, which will vertices naturally, but also it will contain a queue. And I'll probably leverage what's the library? Is it DQ? There's some queue library. Can you remove, from the primitive list, is it like C where you can just like remove, because normally if you use like the inbuilt remove in Python, can you remove an element from the list without shifting all the other values down? Like I don't want the indices to change, you know what I mean? Okay. I understand. I must use a different data structure. Oh, okay, yeah, fine. Yeah, but Oh, swapsies. Swapsies are smart. I respect that. Wait, so what? Wait, did I have a problem? Why did I have a problem with dictionaries? Maybe I didn't. Maybe a dictionary is fine. Oh, the only thing was because like if I want to iterate through all the nodes or something. Wait, I can iterate through all the nodes. That's not hard. Dictionaries are pretty well written in Python, so like iterating through them is pretty comfortable. Um, yeah, okay, that's probably easier then. Ignore that. Use a dictionary where each ID. I think the only thing was how do I decide what the ID will be? Because obviously I could just keep a count of vertices. Every time you delete a vertex though, you'll just have holes, I guess, in the ID numbers. Like, you know, you have 1, 2, 3. You delete 4. You delete 2, sorry, and you create 4. Like, you won't reuse the 2 ever again. That's the only thing that's a bit annoying, but that's not a big deal. Again, small application. Okay, fine. We use a dictionary. That's what I normally do anyway, but I just figured, I don't know, didn't feel clean, but it's clean. It's fine. 1, 2, 3. So each of these indices links up with a vertex object. So this is basically my vertex set, basically, this dictionary. And each vertex talks about its neighbors, which is fun. And that tells me who you're joined to. And the idea is if y exists in x.neighbors, then x should exist in y.neighbors because of the undirected nature of the edges for now. I know that. That's fine. Vertex, neighbors. Yes. Am I missing anything? I'm not caring about this anymore. This idea is stupid. And yeah, okay. This should be enough then, surely. So we'll pass this for now. Class vertex. So do I give it? I guess. Yeah, I guess I don't need an ID because the ID basically comes from there, right? But maybe a bit of redundancy isn't a bad idea. Def, so your constructor call, pass the ID. Self dot ID equals ID, and self dot neighbors equals a set. Can I say what the set should be? Can I be like set of vertex? Can I do that? Is that legal? No. Oh wait, it wouldn't be here. What am I doing? It would be here if anything, right? Does that work? Some kind of typing. Cool. Oh, I spelled neighbors wrong. That's fun. Okay. I mean, there's no real need for getters and setters because Python is Python. Graph. Okay, so def init self. So yeah, the constructor will naturally just have an empty graph, I guess. Self dot, I don't know, vertices. Should I call them nodes? Is that better? Nah, vertices. Equals empty one of these, and then basically def add vertex. Maybe it's good to have self dot num vertices equals 0. Although it's the same thing. Actually, if I do length of vertices, that'll tell me that anyway, right? Add vertex. Again, do I need to give the? Nah. Or maybe like I'm just thinking like could I give it like a name? Like give a name to a vertex, like a string. That I expect to be unique somehow, but that would be annoying. That'll be interesting. For now, just leave it. I would say don't worry about giving it. So the length of, my ID will be the length of the self dot vertices, and then self dot vertices at the ID is equal to a new vertex given this particular ID. Fantastic. And then def add an edge, self v1 v2, both of these should be of type vertex. So first check existence. If self.vertices.get v1 none, or v2 none. So if this is none, so if not this, or not this, then, wait, can I also just do that? This will return true, if this returns true and this returns true. So, wait, my Boolean algebra is failing me. So if this returns none, false, and false, and then not will make it true. No, but if either of them, I'm trying to be too clever, let's leave it. If not this or not this, yeah, that's fine. What, raise? Oh, what did I just do? Oh my god. Oh, I did the thing. I forget how to do that, but I did it. Wait, what? Oh, I see. I'm stupid, sorry. Raise vertex. And otherwise, should I just have like def add neighbor self vertex, yeah, neighbor self dot neighbors dot add this guy, what do I call it, name, def remove neighbor self nay vertex self dot neighbors dot, there's a thing where it's like remove throws an error but delete doesn't, or discard doesn't. Does not raise, yeah. Like, do I care about surely not, right? So I'm basically just method forwarding. Like, I could just write this every time, but this feels cleaner somehow. Otherwise, self dot vertices at v1 dot what was I doing? Add the neighbor, right? Add neighbor. Okay, fine. I'll do it like this thing. Vertex 1 equals self dot vertices at v1. Vertex 2 equals self dot vertices at v2. And then v1 add vertex 1 dot add. Okay, what I'll do first actually is just type this. So was it dict int to vertex? Is that how you do it? There you go. Add the neighbor vertex 2, and then vertex 2, add the neighbor vertex 1. So that's fantastic. That's how we assume undirected edges. Don't need that comment. I'm just keeping this in to keep track of my assumptions. Bing bong, that's fine. That's also fine, I think. Okay. Um. Now, I didn't really. I don't really have a source node. Like BFS, you normally think of having a source node. Wait, let me tick things off actually. So I've basically been able to create a node and create an edge, right? I have to remove stuff actually, yeah. Def remove an edge will be easier. So self. Ooh, how do I do this? The edge between v1 and v2 is probably easiest, right? So, ooh, same kind of vibe. If not that, raise that, and then very similar. And then, yeah, like vertex 1 dot, what the heck happened? Oh, vertex 1 dot remove a neighbor, vertex 2, same vibes. So very, very similar. Is it worth? Nah. Vertex 1 is equal to this one, vertex 2 is equal to this one. Very, naturally very similar functions, just doing the exact opposite. Alright. Remove a vertex. So this is where things get more awkward. I need to be given a particular ID. V1 V integer. So if not self dot vertices, v1 none. Not v1, just v. Raise vertex not found. Otherwise, vertex is equal to self dot vertices at v1, and then I keep doing v1. It's because I'm reading the line above. I'm like copying myself. Okay, so how do I want to play this? Neighbors equals vertex dot neighbors. All right, so I'm getting the neighbors. For n in neighbors, n dot remove neighbor vertex. So this is me like erasing vertex from the existence of all the other nodes as memory, basically. And then I don't even need the variable, to be honest. So that's that, and then after we do that, we can basically just completely delete our length isn't going to work, I just realized, because the length will reduce when you delete, and so you might double up on IDs, so I need to be careful. I'll think about that. For n in vertex, n dot blah blah blah. And then, unless I literally don't delete it and I just go self vertices at v is equal to none, because then the length will always stay non-increase or non-decrease. Like it will always stay, it will never decrease. In which case, the IDs will always be the next big number, and it won't. Like the risk is basically, hang on. The risk is, let's say I have, in node 0 is equal to this vertex, and then vertex 1 maps to this guy, vertex 2 maps to this guy. So the way I would normally figure out the next ID is I say, well, the length of this guy is 3. So I'll take 3 as my next guy. And now the length of this guy is 4. The number of elements is 4, so 4. If I delete this dude, let's say, and try this length business, the length is 4 again. So I'll take 4. And now I have a clash between two different vertices, but with the same key. So one will get overwritten. This one will get essentially deleted, and that's bad. So instead of fully just deleting, if instead of pop or whatever, the remove, instead of using the remove method, if I literally set this to none, like this line is saying, this line, then the size will stay 5 in this case. 6? 5. 5, sorry. The size will stay 5 because even though it says none, like this, the key still exists, so then I will take 5. So the size of the dictionary will never change. Or will never decrease properly. Like the length will always stay non-decreasing. However, is that a good idea fundamentally? Like, do I really not want to delete nodes that I deleted, basically? I think I do. So in that case, I could just do like a global counter. Call it the next ID. Whoa, I did it again. How did I do that? I don't know what I'm pressing. I'm just... What? No. What did I do? I just want to get out of here. Okay. I don't even know what I'm pressing. I'm just like kind of... Because of the drawing tablet, like my arms are further out than they normally are. So what do I say? Just do a counter. Self dot num, like, just like a next ID, we'll call next ID equals set to 0, and then add a vertex. ID equals self dot next ID, and then self dot next ID plus equals 1. Damn, if only we had plus plus. Yeah, and then if I do that, then I think I should be safe to basically be like self dot vertices dot... Is it pop? Yeah. Pop this particular V. Ew. Sorry. Yeah, okay, so we can add a vertex, we can add an edge, we can remove a vertex, we can remove an edge. Yeah, and then BFS. Where we're pretty oh, see, but if you delete 0... Okay, here's what we'll do. Def BFS self. If the length of this guy self... This is why we need to make sure this is why we have to remove it, because if we don't, then we won't know how many vertices we have. If the length of self.vertices is equal to 0, so if not this, then do I raise an error or just be like, yeah, fuck it, raise no nodes to apply, sorry, no vertices to apply BFS. Breadth first search. Otherwise, we have at least one node, so then we just take one, right? So can I like peek at a dictionary? Probably not, right? I just want one element. It doesn't really matter which one. 4? No. Self.vertices dot... Just get all the keys and just take one. Get. Yeah, let's go through all the keys. For key vertex in, there's a thing you can do, right? Dot, is it items? Because there's keys, and I think there's values, and I think items is like the pairing of the two. What? Where does the doc turn a set like object providing a view of the items? I think this is right. Hope it's right. Source equals key and then break. Because like the thing is, there's no sense of indexing a hash table, so like can you peek at one element in a dictionary? Yeah, you literally have to like. That's funny. Okay, yeah, I guess random was a bad word to use there. Okay, and then I need to. Okay, import Q Python. I always forget exactly what the thing is. Is it just Q? No. I want the one that's and has this stuff. Could be good. From Q import Q. Thank you. Do I just make a list or what? Oh, right, that makes sense. Q equals Q. Max size would equal the length of self.vertices.keys. No, self.vertices, that's fine, that's enough. So we got the Q. Q dot is it put? Yep. The source. And then while Q empty. Psych. DQ. Get. Sure. Current. Can I be like, this is a queue of vertices? Is that legal? And then we'll know that color is a nice. Alright. For neighbor in cur.neighbors. So we've got to be careful because the end goal is to use this to help with drawing. So even if I've visited, I need a visited set. Q and then visited equals set. Visited.add the source. We did this beneath. Whoops. I want to make sure, like, even if I this will be like draw the edge or whatever. Regardless of if it's visited or not. But if neighbor is in visited, then you should continue, I think, because BFS's goal is always to find the shortest path to each node. So if it's already in visited, you don't want to be using this new way of getting to neighbor. You don't want to be using it because it's a longer path. Otherwise, add it. So visited.add neighbor. This is different to DFS where you add to visited, I think up here, like after you DQ or pop off the stack. Visited add and then q.put the visited. No, not the visited. Put the neighbor. And then you're always popping off the queue. I'm dequeuing, I mean. You're always dequeuing. So then this should eventually terminate because there's only so many nodes you can add. Hopefully that's fine. And then what am I actually trying to do? Otherwise, draw the node. If the neighbor is invisited, then you should be able to draw the edge. Otherwise, draw the node and then draw the edge. So this is like kind of what would happen applying BFS. Bearing that in mind, this BFS might not even go to the graph thing. BFS might go to like a separate class, like the drawing class, right? Because that's what's happening. Interesting. What's the time? 10:18. I should go to bed. Okay. Let's just test some stuff, just to make sure I didn't absolutely mess this up. Name equals what? It's this, right? G equals graph, and then G dot add vertex. Do that a few times. I should really have more printing. I just realized, like, it's not actually obvious what the IDs are. Maybe I'll return the thingy. Add a vertex. Created vertex with ID equals ID. Created edge between vertex v1 and v2. Put a little tab in there, just for style points. Print deleted vertex v. Print deleted edge between. Okay, and then in terms of BFS, what's the best way to do this? Like before I actually draw it. Like, what's this? Just to make sure that my BFS is running correctly. I'm pretty confident. I mean, I've implemented this a fair few times, so I should be fine. But could have missed something. You never know. Happens. DQ'd Alright, so add some vertices, so then we'll call this like ID1, ID2, ID3, ID4, ID5, and then G dot add an edge between ID1, ID2, ID1, ID3. ID2, ID4, G dot add edge, ID4, ID5, G dot add edge, ID3, stochastic stuff. I'll have like a summarize just for some more logging. For how do I want to do this? Key or ID vertex in vertices self dot vertices dot items. Print ID vertex ID print neighbors for n in v.neighbors print n dot id, I think. Yeah, should be fine. Okay, so then we'll just like remove a couple of it, like remove an edge between, we'll say like, oh, we added an edge between ID 3 and ID 4, but then we're like, oh, actually, it's like that bridge never got built or something. And then g dot remove vertex, ID 3, right smack bang in the middle. And we'll just do the printing thing. So g dot summarize before and after we remove stuff. No c lowercase. Oh, very good. Vertex is not defined. Is that because? Fair enough. I respect that. I mean, I could just get rid of the typing, but I'd rather not if I can help it. Can I be like... I can't define it twice, right? Oh, it kind of worked. Created with ID 0, 1, 2, 3, 4. Create an edge between 0, 1, 0, 2, 0, 1, 0, 2. Maybe I should call these like, maybe I'll just call this ID 0. Just to match with the actual ID values. ID1, ID2, ID3. Did that not work? That didn't work at all, did it? ID4, 0, 1, 0, 2, 1, 3, 3, 4. We'll say 4, 5. Oh, right. 2, 4, 3, 4. Or something like that, right? Oh, I already have 3, 4. 1, 4. And remove 1, 4. And then remove that vertex. What was the error? Oh, whoops. Should say get. Wow. Okay, so this is like before the deletion, this is after. So let me just look at what I actually did so I can figure out what it should say. So you got 5 vertices. This is 0, 1, 2, 3, 4, and then 0 and 1 have as an edge. 0 and 2 have an edge. 1 and 3. 1 and 3, 3 and 4. 2 and 4. Let's change colors real quick. 2 and 4. 1 and 4. Okay, so that's after that. And then, so the neighbors of 0 are 2 and 1. Good. Neighbors of 1 are 0, 4, 3. Yes. 0 neighbors of 2 are 0 and 4. 0 and 4. Neighbors of 3 are 4 and 1. Very nice. Neighbors of 4 are 2, 1 and 3. 4 are 2, 1 and 3. Good. Deleted the edge between, okay, yes, and then looking at the instructions, we remove the edge between 1 and 4. Remove the edge between 1 and 4, and then we got rid of vertex 3, which means, wait, what? It says I have the eraser, but it looks like a pen. Okay. Which means we got rid of the 3, which means we got rid of its edges as well. Wow, that's actually quite a bad graph. So you have vertex 0, which goes to 1 and 2. You got vertex 1, which is just 0. You got vertex 2, which is just 0 and 4, and then this is 2. Okay, yeah, looks decent. Obviously, if you're a big man, you test it properly, but I am not, so. Okay, nice and easy. I could try, I guess I could try the BFS actually. I'll get rid of all this extra printing. And then BFS, g.bfs. No. There's no attribute called ID. What? Does that make sense? Well, IntelliSense doesn't seem to think so. Unless the reason is because... Ah, bro, what am I doing? Wait, okay, I need to figure out if I want the queue to have vertices in it or it's because I put an integer. I'm dumb. What do I want? Okay, we'll do integer. Just because we have a lookup table anyway, can't be that big a deal. Car ID. What the queue? No, what am I doing? The self.vertices dot get car ID. Cool. And for neighbor, incur neighbors. If neighbors and visited, continue. Visited at the neighbor. Yeah. Is this a set of? It's a set of vertices. Okay. Is it better to have a set of IDs for space reasons or? It's probably their addresses anyway. Neighbors and visited. Alright, try that again. No. For and current neighbors. Ooh. Delete dequeued 0 and 1. You did it again because you queued the neighbor, not the neighbor's ID. Okay, you got to figure out what you want. Do you want this visited set to have? I need to figure out if I want the. Oh, so wait, so okay, so the typing isn't actually that strong. I thought it would actually like blow up in my face if I tried to add the wrong type, but I guess never mind. It's more just for IntelliSense and your own reading, but the Python interpreter won't give a shit. Fair enough. I respect that. Put the source visited this one while it's not empty. Get it. It will give me the ID for each neighbor. Do this. I mean, I guess we can make it all integers. Make these guys contain integers as well. In which case, if neighbor.id is in that, then do it. Otherwise, add the ID, put the ID, and do all that, just to keep it consistent. So, based on the fact that I'm assuming we've started at 0, you go to 0. Whoa, didn't know me to do that. You start at 0. You would enqueue 1 and 2. That's what happens. You dequeue 2. Oh, you did 2 first. Fine. Okay. I respect that. 2, 1. You dequeue 2. So you're kind of here at this point. You would enqueue 4. You dequeue 1. Visit. Has nowhere to go. And then you dequeue 4. Fantastic. The only thing you have to be careful of in terms of the drawing is, like in this case, when you dequeue the 4, this green edge would have already been drawn, so there's no need to draw it again. So how would I keep track of the fact that I've already drawn something? Oh wait, no, that makes sense, yeah. Because if 2 is already visited, no, but you don't know that the reason you visited 2 is because you came from 2. Okay, hang on. Okay, I need to use the fact that it's BFS. So 0 to 1 and 2 as well, and then 2 to 4, 4 back to 2. I could simply, like, in terms of in the drawing class, I could just keep a set of like all the tuples, and then be like, oh, if this edge that is described by these 2 vertices is already in the set, then don't bother drawing it. Like, it could do it like that, just use more memory. But is there a clever way? Because the fact that BFS goes from here to here, and then here, 1, 2. So like, let's say we have like a bit of a cycle going, right? Let's say there's like in node 5, and it's like a big cycle. 0 happens first. It enqueues 1 and 2. Let's say 2 gets dequeued first. Then we enqueue the 4, and only the 4, because only the neighbors, right? Then 1. We go here, and then from 5. So at this point, we would have drawn this edge, and this edge, right? And I guess we would have drawn this edge because we would have seen the 5 and gone, hey, we haven't done this yet. We would have drawn the edge on the thing. Then from 5, I would see both of these and say, hey, both of these are already visited, but this edge hasn't been drawn yet. So I would need to know to draw this edge and know not to draw this edge, because this edge has been drawn, this one hasn't. So the way I would do that is by recognizing that what I could do is say, well, the node that I just came from 5 was 1. And this 5 is only going to be visited once, right? That's the beauty of these traversal graphs, traversal algorithms. So if the thing I just came from was 1, then all the other edges that are, in 5 or whatever, would not have been drawn yet, I think, regardless of if the nodes that they lead to have been visited. Because if this guy has been drawn, and that's how we got to 5, then at no other point would, for example, 4 have gone to 5? Because 5 would have already been marked as visited when we went from 1 to 5 and we drew this arrow. So then, if on top of the neighbor's value, if we keep track of the node that took us there, the previous, not the, what's it called? What's the array called? Predecessor array. You can either have a predecessor array, or I think it would also work just to, in your queue, have tuples, which might sound the same as doing this thing of just keeping track of all the sets, keeping track of all the edges you've drawn. But I think the difference is you kind of have to hold on to this set for longer. This set you have to hold on until like you've finished drawing, whereas with this way, you would be like popping things off, and like your queue size would be like shrinking even as it growing, you know? Whereas this set would only just be growing. So I think it makes sense. In your queue, keep track of, you can also have a separate predecessor array. That's actually how you describe the shortest path in BFS, right? You keep track of who was the guy that led to you as a vertex, you know? The predecessor of 1 is 0. The predecessor of 2 is also 0. The predecessor of 4 was 2. The predecessor of 5 would not have been 4. It would have been 1, because 1 gets to 5 first. And then, since 1 is the predecessor of 5, this edge I think you can guarantee this edge would have been drawn. Whereas 4, you know, wouldn't have been drawn because it took too long. So I think the predecessor array is a good shot for drawing specifically. You know, if you actually want to, and if you want to illustrate the shortest path as well, you'd need a predecessor array. So yeah, I do think that this was actually kind of not what you should, like, I don't think I need to write DFS inside the graphing class. I think it would be in the drawing class, which I will do. I can go for another 10 minutes or 20 minutes. All right, so graphing. The draw graph.py class draw graph. I don't really know how to do this. Import tkinter, right? That's all fine. Very nice. Is tkinter built in? I forget. It must be, right? Like, do you have to download tkinter? Class draw graph. How do you even do this? Something about a window? Alright, I should Google some stuff. Hang on. I haven't used tkinter in ages. Tkinter Python creating a window. Is that like a Geek for Geeks thing? Yeah. Come on. As TK, I forgot about that. It's like typically what you see. So def like render a graph given a particular graph, and then root equals tk.tk. Can I do that inside here? Wait, what? Oh, root equals, sorry. Root equals tk.tk. So top level widget represents mostly the main window. Ah, so that's the window. Oh, that was easy. Okay, so that should create a window, I think. And then, yeah, cool. A label. So what do I want? I basically want to be doing DFS. I don't want that. Yeah, self is going to be a problem. Whoa. Oh, I'm not in insert mode. G, can I basically just replace all the selves with Except the first one, obviously. Yeah, I can. Okay, so the only thing is, I can't remember. I think widgets do have widgets are objects, right? So they like their positioning and stuff will be easy to find. The only thing I have to remember is, I guess I would probably want like maybe a separate hash table that basically keeps track of like the vertex. It would be like a dictionary that takes in an integer, but then instead of a vertex straight up, it would be like a vertex widget, whatever that is, like a box or something. So I might need to do something like that. Source is this one, so it's the same kind of vibes, but I have my queue, which is this one. I have this one. Oh. I'd have to be able to like get the frog. No, get the position of the neighbor vertex widget first, and then I should have enough information to draw the thing. Otherwise, figure out a relatively clever position for the node. So figure out a suitable position for the node. Draw the edge. Current ID. Okay. Let me just figure this out. So label? I don't really want a label. I want like just a normal, just a rectangle basically. A circle would be better, but okay. How to draw a circle widget. It's drawing circles. Oh, interesting. This was not what I expected. I need to create a canvas. Ah, that's worse. The reason it's worse is because the canvas widget will have positioning information, but this one will not. Interesting. Yeah, so I'm gonna probably have to figure out a positioning algorithm, like something to figure out where the next guy should go. Oh, okay. I'll read up on that then. Alright, that's fine.